Hello, good evening. Today is December 26th, 2020, and I'm continuing with the video presentations. Over the last, I believe, 7 months, I have been videotaping the keynote presentations I've been giving, around 17 of them over the last 7+ months, actually since March. So it's almost 9 months since we started working from home during COVID-19, and also some of the panel presentations, as well as some other key presentations, important presentations I've given. So between now and end of this year, so over the next 4 days, I'm going to tape a series of presentations. And these presentations are some important presentations I've given over the years. Some were given in 2013, some even before that, and some around that time. So, so today is the first of the series of about 4 or 5 presentations I will be giving. And so today's talk is at a very high level. It's on malware, which is malicious software. We are hearing so much about malware over the last probably 10, 15 years. And this is a lecture I gave in 2013, April. And this lecture was given at the University of Texas, Dallas. It's a very distinguished presentation called Polykarp Kusch lecture. Polykarp, I think it's P-O-L-Y-K-A-R-P. Kusch is, I believe it's K-U-S-C-H. So it's a very distinguished presentation. And every year, the university president and provost invite one person to give this talk around April. And so I was selected to give this lecture in 2013. And so that's the lecture I will be giving now. And so what I'm going to do now is share my screen. Okay, so sorry about all these advertisements. Okay, so my talk, and as you can see, it was given on April 19th, 2013, as part of the Polykarp Kusch lecture series. And so my talk is on reactively adaptive malware. What is it? How do we detect it? Okay, so this particular lecture is usually given for the various donors of University of Texas at Dallas, as well as some executives and senior administrators, as well as some technical people, but it has to be at a high level so that everyone can understand. And what is interesting about this lecture is that since I gave this initial lecture in April 2013, I have given these variations of this talk, essentially based on this lecture, quite a few times at public libraries and various other events for the general public, such as the Subcontractors Association. So I'm going to continue to give this lecture because, when you talk about malware, right, it's, whatever has happened, just because something's happened, say in 2008 or 10 or 11, it doesn't mean that it ends, it continues. So I keep adding information as things happen, attacks happen in the real world. And so especially during COVID-19, I think we're also so concerned about our health that we often forget about cyber hygiene, right? So I'm going to talk about that at the end after I talk about this, after I give this lecture. So let's get started. So I'm going to draw some analogies, okay? And then explain what is malware and what are our solutions. It's a team effort. Myself, my colleagues, Dr. Latifa Khan, Professor Khan, Professor Hamlin, Professor Lin, who is now at Ohio State, Professor Makris, and then Professor Cardenas, who is now at UC Santa Cruz, and Professor Kantarji. So we have now several new professors who have joined our team, and they do some very interesting work on malware. And so right now, one of the hottest areas, or one of the most popular areas, is applying data science, machine learning for cybersecurity, and what happens if the cybersecurity techniques are attacked. And I'm not really explaining, especially the latter topic, what happens if the if the machine learning techniques are attacked, what happens, right? So that's a very big concern. And I've given a number of talks in some of my previous lectures that I have videotaped. So if you go to my YouTube channel, by the way, I'm going to post this on YouTube under my channel. So I've given a number of talks on what happens if the machine learning and data science techniques are attacked. So our solutions, and then what about the directions? So I'm focusing, I'm saying we need a holistic interdisciplinary treatment, right? That is what we need. Okay, so analogies to the human body. Humans infected with virus and bacteria, right? Little did I imagine when I prepared this talk in early part of 2013, what we are going to be faced with barely 7 years later in 2020, right? One of the worst pandemics in centuries, right? The last time something like this happened was 100 years ago, the 1918 Spanish flu, which by the way did not start in Spain. So no one knows exactly where the Spanish flu, where it started. Some say it's Kansas, some say it's somewhere else. But in any case, now we are faced with another major pandemic. So humans are infected with virus. Virus replicates itself and spreads through the body. And one other thing I want to mention, virus also mutates, right? As it's replicating and spreading, and then it spreads to other people. As it spreads, it also mutates. And that's a big challenge we have. And it attacks the vital organs. We know now with COVID-19, it attacks the lungs and also other organs as well. The doctor conducts tests and detects the problem. And of course, medicine is given to slow the progression of the disease. And patient's condition may improve or patients may die, right? That's the sort of the stark reality we are faced with today with COVID-19. So here's the patient, the doctor, and this is the virus. Okay. So another analogy, this time an organization. Bad person joins the organization and pretends to be a good person. We hear so many of the espionage cases, right? CIA, FBI, and so on, right? So they are bad. They go through, for some reason, the clearances, they pass, and then they are pretending to be good and stealing all the secrets and conveying the secrets, sending the secrets to the adversary. So she monitors what is going on and spies on the organization, conveys vital information to the adversary, it's insider threat, builds a network of bad people, takes over the organization. Okay, so that's, again, these things happen. So that is what we are faced with today with malicious code. Just like the organization or the human body, we have now malicious software called malware. It's a piece of software that is malicious and carries out bad things. It infects a vulnerable and neglected machine, just like coronavirus, that coronavirus, SARS-CoV-2. That's the virus that is attacking the humans, and it attacks the vulnerable people, the older people, those with pre-existing conditions, right? And especially, people who have neglected themselves, who've got diabetes and cancer, unfortunately, or various other conditions. So it attacks the various components of the machine, the operating system, like the vital organs, the applications, which you can think of as the limbs of the person, and the hardware too. That's I call it the bone. It spreads across a network of machines, just like people, right? COVID-2 coronavirus is spreading, right, across various people. It cripples the machines and the network. So it cripples the people, conveys vital information to the enemy, right? Whoever has the perpetrator who has planted the malware. It takes over the network and carries out its agenda. As you can see, the virus going and attacking and what it's doing, right? The various cells, right? The victim network. And these are the nodes that have been attacked. Okay, so malware, we used to call it with different names like viruses, different names, and they all had specific meanings. Viruses did certain things, worms did certain things, Trojan horses did certain other things, but now we sort of generalized everything and we call it malware. Okay, what does it look like? What does it look like? Remember back in 1999, I'm sure many of the viewers, wouldn't remember because they probably would have been too young, right? That was 21, almost 22 years ago, March 26, 1999. We had a virus called the Melissa virus. And this is the code. It's just a piece of software. If you look at the code, it's just the, if then else statements and, just like any other software. But what it's doing is something very, very dangerous. It is the malicious code. So when certain events occur, this piece of software is triggered, it executes, and then it can go and read all the files and send information to the perpetrator. So it's just like any other program. And that is what makes it so dangerous. Okay, so that's 1999 Melissa. Since then, we have heard so many various types of viruses. So the virus and the antivirus arms race. So you can think of it as the coronavirus and sort of the vaccines, right? The antivirus, the vaccines we are producing, the medications. It's sort of like an arms race right now. Malware, the viruses, rogue programs carry out malicious action on victim machines, vandalism, it can delete files, carry on phishing scams, reconnaissance and secret exfiltration, cyber warfare, hacktivism, sabotage, attacks against power grids, randomly mutate themselves automatically as they propagate, right? So, and we hear now about the mutation of the coronavirus, right? In the UK, they found, I think last week, right, about 5, 6, 7 days ago, that the virus is mutated and the coronavirus, and it's spreading much more rapidly, right? So randomly mutate themselves automatically as they propagate, harder to detect since no two samples look identical. Antivirus defenses. So these are like the vaccines. Defenders manually have to reverse engineer many malware samples, have got to figure out what they are, find mutation patterns, build defenses to automatically detect and quarantine all mutants. So it's a challenge, right? The doctor and the virus, so the defender and the virus is sort of the attacker. Okay, so incidence reports. I think we first started hearing about this, about systems being, malicious code. I think there were worms, even 1988. Remember, there was this Morris worm, this graduate student at Cornell had, unleashed a worm, and the internet it came to a standstill. So I got to hear about this worms even before that. So I got into cybersecurity in 1985 fall. So I've been working in the field for over 35 years now. And then I used to read a journal called the Computers and Security. It's still around. It was by, I think, North Holland. At that time, North Holland, Elsevier. Now I think it's a journal by Springer. And so that was the first and only journal at that time. And so I used to read articles, and they had quite a few articles about worms. And so it was 1985, and Trojan horses were, that was one of the first things I studied when I was started to work in cybersecurity, right? So, but then we didn't hear until, we had the emails and internet. That was in the 90s, early 90s. So, but when you look at 1990, right, it was hardly anything. Gradually, it sort of increased. And then 2001, you can see what has happened in 2001, many incidences. 2001 was sort of, everything changed in 2001 with the major attack called Code Red. Okay, so now the antivirus industry, you can think of it as a vaccine industry. It's very bad. The problem is much worse now. In 1998, it's almost like we here, the good guys, right? We are in control and we are chasing the virus. So it's almost like we, right, the scientists and researchers, we are in control. We know what vaccines to produce and we are sort of chasing away the virus. And this was sort of in a way the case over the last 100 years since the Spanish flu. We've been improving and improving. But then in 2008, just 10 years later, you can see the virus has taken control, right? The malware, it's chasing us. It's almost like what's happening now with COVID, right? We are sort of scrambling. Yes, we have these vaccines, which is good news, but we don't know what the side effects are. We don't know what the reactions are. Some people are reacting, very few though, very, very few. So there are many unknowns, but still it's very good news. And by the way, as soon as the vaccine becomes available to me, I'm going to take it, right? It's going to be a little while before it hits my age group. And so, but still I'll be queuing. I'll be sort of one of the first ones right there. As soon as they call me, I'll be going immediately to get my vaccine. So, but still, right, we don't know what's going on, right? We are trying this treatment, that treatment, and the vaccine. So that's the situation right now. Okay, so our malware team, this was in 2013, right? So there's, of course, myself, the executive director of the Cybersecurity Research and Education Institute, Dr. Hamblin, Kevin Hamblin. He does a lot of work on reactively adaptive malware and solutions. Dr. Khan, data mining solutions for malware. And then Dr. Lin does a lot of work on Android malware and solutions. He also does a lot of binary code analysis. And Dr. Makris does work on hardware malware and solutions. And Dr. Cardenas does work on smart grid malware, his cyber physical systems. And Dr. Murad Kantajlu does work on adversarial mining solutions. So this is, again, what happens if the machine learning techniques are attacked. So he's doing, so we are talking about that particular topic, but just very briefly in this presentation. So that was our malware team. We still have 2 more professors, actually 3 more who have joined. So 2 have left and 3 have joined. And so our malware team, right, increases almost every year. Okay, so data mining solutions. So I'm going to start with that. And this is Dr. Latifa Khan's work. So what is data mining? So back in 1998, I wrote a book on data mining technologies, techniques, tools, and trends by CRC Press. Okay. And again, data mining, knowledge discovery in databases, data pattern processing, pattern extraction. You have to dig, right, and extract those gold, very precious nuggets. So the process of discovering meaningful new correlations, patterns, trends, and nuggets by sifting through large amounts of attack data, often previously unknown, using pattern recognition technologies and machine learning, statistical, and mathematical techniques. Okay, so that's general definition. So we were talking a lot about data mining back then, but today it has sort of evolved into data science and machine learning and now artificial intelligence. So what do you do for data mining, right? This is one of the techniques that we focused on. Dr. Khan was the main person. I was a PI for an Air Force project, and I worked with Dr. Khan. So essentially, we used classification. That's a particular machine learning technique. So we train data, right? So we use support vector machines. So we take the program, extract binary engrams and assembly engrams. So we mix the binary engrams, binary code and assembly code. We mix it. And then we use the data mining classification support vector machine. And we then test, right? Train and test. I'm going to come back to this box later in a minute, okay? So test, and then we have 2 class. If it's good, you can see the lady smiling. It's a nice, it's a benign. And if it's bad, it's the malware, Okay, and so we developed our own algorithm. We took support vector machines, but we enhanced it so that it can give us better accuracy. It was called DGSOT, Dynamically Growing Self-Organizing Tree, a novel solution. Okay, so this is essentially what happens. You train with some training data, and then you test it. And then is it a good class? Is it malware or is it not malware? Okay, so we had some interesting results. So we looked at hybrid, meaning binary code and assembly code, right? Those of you all who are doing programming, you have the high level languages and the assembly programming and binary bits and bytes, 0, 1. Assembly actually is, move one register to another, move instructions and various things, right? Okay, so hybrid, binary feature set, assembly feature set, right? So table 3, I mean, I'm taking from some of our papers. False positives, false negatives rate. So n-grams, either 1, 2, 4, 6, 8, 10. And hybrid gave us very good. False positives was false negative, I think false positive 5.4, false negative 2.6. Binary wasn't so good. Binary only 17.8, 4.7. Assembly only 24.4 and 3.3 in one data set. Even the other data set, I think hybrid, when you combine binary and assembly, it gave us better accuracy. Okay, so at that time, we didn't know why we got these results, but now hopefully there's explainable AI, artificial intelligence, where it explains what it's doing. So there are, many advances. Hopefully we can get a better understanding how these machine learning systems work. Okay, so that's the data mining for malware, right? But now the malware is changing patterns. So we call it reactively adaptive malware. What is it? The next generation malware technology, where malware that mutates non-randomly, learns and adapts to antivirus defense fully automatically in the wild, immune to conventional antivirus defenses. So it's immune to conventional medications and vaccines. So you can't take the flu vaccine or cold. I mean, there's no vaccine really for cold. It's also a type of coronavirus. So existing vaccines don't work, right? It's a new type of malware. And so you need to develop new vaccines. And that's what we are doing for the SARS-CoV-2. And the thing is, once it mutates, we are hoping that the current vaccines by Pfizer and Moderna are going to work with the mutation, but we don't know, right? We are expecting that it's going to work. So immune to conventional antivirus defenses. And this was also an Air Force project with Dr. Hamlin. So look at this. You have here green, suddenly, next millisecond later, it's purple, then it's turning into blue. I'm just giving an illustration. It's like today I have black hair with a bit of gray. Tomorrow, I could wear a wig and come with blonde hair. And the next day I could come with red hair. Only thing, it takes a while for me to sort of take my sort of wig or whatever and put another wig. Only thing, this could happen in milliseconds. It could change patterns, and we've got to detect, because the antivirus products from McAfee and so on, Symantec, they are not going to find, the malware, the new malware, the mutated malware. So that's the challenge. So this is a very interesting piece of work, because what we are doing here is saying that the malware, how is it going to change patterns, right? It is using, we are saying it can use data mining, right, in order to change. What is the best way to change so that it's not going to be detected? So we have all the antivirus signature databases. So this is the known signatures. And then we have the signature query. And so the malware is querying, and then getting the signature inference engine is reasoning, right? Querying, getting the information, it's doing the approximation, then it's deciding what is the best way to obfuscate. And then it has an obfuscation function. And then from the malware binary, the existing binary, it goes into the obfuscation function. You have the obfuscated binary. You also do testing. Is it going to catch? Is the antivirus signature database, is it going to catch the obfuscated malware? And once it's sure, this is what the bad guys are doing. It's going to propagate. Okay, now I'm not saying the coronavirus is going to use data mining to decide how am I going to mutate, right? So I don't, it's not doing that, but the malware, it's a software program, right? So it's doing that. So, and it's a very interesting piece of work that Dr. Hamlin, because remember, to catch a thief, right, you've got to think a bit like a criminal. But you need to understand what ethical hacking is. That means you need to be able to, develop malware yourself, but you've got to do it in a very controlled environment. So my colleague, Dr. Hamlin, with his PhD student, is now Dr. Mohan, who works for Google, I believe. So they published a paper in the Usenix Vote conference. In 2012, you stitch together code harvested from benign binaries. So it all several benign code, right? It could be application 1, application 2, application 3. Put it all together. It's like Frankenstein. Stitch it together, and then you can get a very potent, dangerous malware. So that is what they developed, and many offensive advantages. Resulting malware is 100% metamorphic, no common features between mutants, statistically indistinguishable from benignware. Everything is plain text code, no ciphertext. Obfuscation is targeted and directed. Evolves to match being infected systems' notion of benign. Okay, so again, the infected system will think it's benign, but whereas it is not, right? So Frankenstein got a lot of coverage, and you can see. So they presented it at Usenix Offensive Technologies. That's the name of the conference, I believe. Thousands of news stories in August, September of that year. Economist, The New Scientist, NBC News, Wired UK, The Verge, Huffington Post, and Life Science. You can see all the, some were very positive and some were negative, because, some people don't like, right, when you start developing, just a second. Okay. Some people don't like that people are developing malware, but then we have to study, right? We have to study malware. So you need to have an understanding how malware is generated. Okay. So how can you develop, techniques, right? That's so like vaccines for viruses that are mutating, right? New viruses. So we have a technique called SNODMAL. Stream is a stream-based novel class detection. So we have developed a technique called SNOD, stream-based novel class detection. It's a patented technique. Divide the data stream. So essentially what we do is divide lots and lots of data coming, right? So network data is a lot of attack data coming in a stream, right? And the patterns are going to change, right? The patterns, it's almost like today we say buy Microsoft, tomorrow buy Apple, the next day buy Facebook stocks, the next day buy, I don't know, Google and Amazon and so on, right? So the concepts are changing. So our system has to be to be able to adapt. And so we, instead of having one model, we have an ensemble of models as the patterns are changing. And then these models will, collaborate with each other and decide which models we can throw away because they are no longer sort of valid, because they are sort of old, and old meaning they are outdated, right? So divide the data stream into equal sized chunks, train a classifier from each data chunk, keep the best L such classifier ensemble. So collection of models. So you can see no DI may contain data points. So essentially, if it doesn't fit into one model, we throw it into a buffer. So labeled chunk, unlabeled chunk. Over time, the unlabeled chunk can become a labeled chunk. So you can see that D1 data chunk as classifier C1, D2 as C2, D5 as C5, and ensemble C1, C4, C5. I think we have thrown away something, so you can see. So in time, so next time maybe D2, classifier C2 would go away, right? And then it will be replaced maybe by C7 or whatever. So that's our whole idea. So what we are saying is, since we are detecting this novel class, unlabeled chunk, so if we cannot classify this malware, we are saying maybe, we can apply this technique. But unfortunately, now 7 years later, we haven't been very successful because we don't have all of the classification and the malware data that's changing patterns. So we have insufficient data to train and test our algorithms with respect to malware. So we developed this technique for NASA, and we looked at all the faulty reports for spacecraft. And so that was, detecting faulty reports. So can we detect malware? And I still believe we can, right? So a new class comes in, and that class can detect this novel malware. A novel class can detect the new malware. So that's our premise. Okay. So it's not just network data. Smartphones, very, very dangerous. We are all now carrying smartphones, almost every one of us, billions of smartphones. Smartphones can also be infected with malware. So we had a project from the Air Force. Okay, so this is again between 2011 to just in 2011, right? From July to November, you can see the increase in the malware attacks in smartphones, like Trojans and various types of attacks. So, and this was also a project from the US Air Force. Solution combines static analysis with dynamic analysis. So this was again a patented technique system. Static analysis, we apply data mining solutions, great, right? So you have malware application, you have all the remote server, the behavioral apps behavior, you have the network behavior, collect all that and static analyze using data mining. And then add to it, because that alone is not sufficient to detect everything, carry out dynamic analysis, the platform, Android and iPhone, and do some reverse engineering. So the calls level, system call, operating systems, networks. And so we had some very good results, and it was one of the early systems that we developed. And so again, as I said, it's a patented system. Okay, now, up to this point, I've talked about software. We cannot forget about hardware. Do you trust your chips? So Dr. Bakris is an expert in hardware security. So the hunt for the kill switch, a IEEE spectrum in 2008, right? So you have the hardware can be attacked, and he's been funded by NSF and at the time Army Research Lab. And so we have a very strong hardware security team. And our solution to hardware Trojan, it's thought Trojan hardware in wireless ICs, analysis and remedies for trust. So this is Dr. Makris's work. And so you can see the analysis, phase, design, implementation, and impact of Trojan hardware in wireless integrated circuits, limitations of manufacturing, test and existing hardware, Trojan detection methods. So we current methods are not working. So then we develop some new methods. So you have the transceiver, the encryption, 128-bit AES. I think 128, yes, AES is a 256. So I think they use 126, processing control logic, storage, and then you come up with some remedies. Preventive methods for shielding against Trojan hardware insertion, Trojan hardware detection methods based on statistical analysis and machine learning. So machine learning is being applied to hardware security as well. And so I'm not really a hardware person. And so again, Dr. Makris is a hardware expert, right? So detecting Trojans in hardware. And that's not all. If you think that's all, okay, software, hardware, that's it, we are done. No, it's now our critical infrastructures, our power grids, our pacemakers, the transportation systems, the Internet of Things, right? I'm not talking about IoT in this presentation because IoT was sort of just beginning at the time. So attacks to critical infrastructures, that's where Dr. Alvaro Cardenas comes in. So the attacks are Maroochydore in 2000, as early as 2000, the HVAC, heating, ventilation, air conditioning, 2012. Everyone has heard about Stuxnet in 2010, and the smart meters in 2012. And you can see, right, all of these cyber physical power grids could be attacked. The threats, remember it was 2013 at that time, Obama administration demonstrates attack to power grid in February 2012. DHS and INL study impact on cyber attacks on generators. So you can see a US video shows hacker hit worked on power grid. Okay, so what do we do? So new attack detection mechanisms by incorporating physical constraints of the system. So more recently, I did some work with Dr. Cardenas. We supervised a student and we looked at Internet of Transportation systems, and physical models are most important. So you need to work with physicists and electrical engineers and control systems folks. So Dr. Cardenas is an expert in control systems. And so he comes up with all kinds of very interesting models. First step, model the physical world with all this, velocity, and when it comes to Internet of Transportation, the velocity, the moments of inertia, and so on. So for a power plant, right, the power grid, there's also the physical model, right? So the first step is model the physical world. Second step, detect attacks, compare received signals from expected signals. So in some of our work, we have used the work jointly with Dr. Cardenas, we use Kalman filters. And then third step, response to attacks, right? Physical world, and this is the model, right? So the model is really a system of differential equations, right? That's a physical model. Detect the attacks. You can see the disturbances, the plants, the controllers, the linear models. You look at the disturbances, right? And then third step, response to attack. No attack, use real plant signal. And then intrusion detection detects attack, IDS system, switch to linear model, detection time, false alarms. And then fourth step, do a security analysis. So once you detect the alarms, have you missed anything? Missed detections, study stealthy attacks, false positives, ensure safety, and automated response. So this is, again, we cannot forget about the power grids. And now we also have Internet of Things. It never ends. We need to understand the adversary, because adversary, this is the adversarial machine learning. Today it's called adversarial machine learning. We call it adversarial data mining at the time. Adversary is trying to find out all about us. What is the data we are using? How are we trying to, what is the model? We are machine learning model. So, and once it's learning, adversary is changing its behavior to avoid being detected, right? So look, it's put a mask on. Data miner, we, the data science experts, and the adversary. So we are trying to thwart the adversary is trying to modify its behavior. We are trying to thwart the adversary and trying to do some modifications. So we looked at support vector machine and how can we modify the support vector machine so that the adversary doesn't suspect. So it becomes game playing, right? Remember, earlier I said malware detection is a two-class problem, good class and a bad class, right? So bad class is malware, good class is benign program. Adapt your classifier to changing adversary behavior. So that's our approach. Questions, how to model this game? Does this game ever end? Is there an equilibrium point in the game? So do we play what game? Zero sum or Stackelberg games or Bayesian games? So that's the challenge. Our solution, game playing. So Dr. Murat Kantarjulu, an expert in game theory, adversarial Stackelberg game. Adversary chooses an action. After observing the action, the data miner or the machine learning system or the data science system chooses a counteraction. The game ends with payoffs to each player, right? Adversary may use malware obfuscation. Remember, I talked about obfuscation earlier. Change has some cost to the adversary, so that the adversary wants to change. So again, adversary, nothing comes for free. So adversary may not have enough money, right? So it's a cost to the adversary. So we need to take the cost into consideration. But again, when you talk about nation states playing these games on each other, right? Nation states can afford, most rich nations, especially, they can afford to do obfuscation and modify their behavior. So in our model, we do bring in the cost, we bring in various other aspects. So we need data mining techniques to handle the changes by the adversary. It was funded by Army Research Office 2012 to 2015, our first phase, and then we are still continuing some work. And my colleague, Dr. Murat Kantarjulu, is the PI. Okay, so this is my last chart. Where do we go from here? Right? What do we do? So I talked about what is it, what do we do about it, and now where do we go? So we need a holistic treatment. You can't have just, take care of one, like your diabetes, and then not taking care of something else, right? So you've got to provide a complete, so holistic treatment, the doctor will tell us for holistic treatment, it's not enough just to take medicines and so on. We've got to be careful of our diet. We've got to be careful of do daily exercise. And we've got to, meditate and get enough sleep. We have to do all that. It's not easy. So 3 actors interacting with each other. The doctor, so corresponding to the doctor is the defender, the analyst, the person who is developing these systems. The patient, who is using the system. Okay, patient is the customer. The customer who is using our systems, we develop like a soldier and the user. And of course, the bad actors, the virus, the bacteria, that is the malware, the attacker. So an integrated model that represents the behavior of all of these actors. That is what we need. And we are doing some interesting research. It never ends, right? It's going to, there's work for us I don't know. I thought maybe when quantum computing comes, but no, because quantum computing or quantum cryptography, I thought that will solve our problems. No, because quantum computing could break the code for quantum cryptography. So what do we do? So again, that means we have to be vigilant. An integrated model that represents the behavior. So together we are doing a lot of work with other schools within University of Texas at Dallas. So we are in the School of Engineering and Computer Science. We do work with the School of Management, School of Economic Policy and Political Sciences, School of Brain and Behavioral Sciences. So we've done some interesting work, interesting papers. And then one other school we work with in statistics, School of Natural Science and Mathematics, NSM. So together we are proposing an interdisciplinary approach. And so towards this end, we've also got an interdisciplinary master's program. So actually this ends my presentation. And so I just want to talk a few things about some of the things that we are doing. As we said, it's interdisciplinary. So we work with risk and decision scientists because risk is important. If we have no risk at all, then we don't have to worry, right? So risk is important. So we work with risk and decision scientists. We work with game theorists. We work with policy experts because policy is really important. So we have Dr. Cardenas, and we work with Professor Jennifer Holmes. She's a dean of the School of Economics, Policy and Political Sciences. She's one of the top experts in policy. So they work together to looking at the power grids, the attacks to power grids in the country of Colombia. And so what I'm saying is we've got to work, it's an interdisciplinary approach. Brain and behavioral sciences, they look at how the hackers think, right? So study the minds of the hackers. So they are an important aspect. Statistics is really important for data science, machine learning, and so on. So it needs a sort of an interdisciplinary approach. And so that brings us to the end of my talk. But the one thing I want to talk about is that, we have this problem now, right? COVID-19, the disease, and the SARS-CoV-2, which is the novel coronavirus. And so we have to be very, very vigilant in the sense that the attackers, the cyber attackers, because we are so preoccupied now, with having to wash hands and with having to, wear our face masks. And so today, usually in the afternoons, especially when the weather is good, I drive to our university and take some long walks because I live in a more, not in the downtown, but it's sort of in a more congested area. So I go there and then take long walks. And then of course, when I do that, I've got to make sure that I have, all the gloves and the mask and then the goggles or at least sunglasses. And I also have a face shield. And so we are so preoccupied with that we may not spend enough time. And then of course, any extra time we have, right, we want to take care of our health. But then what about cyber hygiene, right? We need to make sure that we are backing up, we are encrypting, all of that. We need to make sure that we do that. And so, and this is especially the time that, the hackers can, because we're so preoccupied, the terrorists can attack us, the hackers can attack us. So this is the time that we've got to be vigilant and do everything we can to protect ourselves. Of course, life is most important, right? We don't want to get COVID-19, but we also have to think about our safety in general and also our cyber safety. So that's one of the reasons that I wanted to give this presentation. And as I said, we've done a lot since then in the last almost 8 years. It's going to be 2013 April, so 2021 April is going to be 8 years. Especially in adversarial machine learning, a lot of work there. We've done a lot of work on binary code analysis for malware. We've also done a lot of work on cyber physical system security, especially Internet of Transportation systems. And so our work never ends, just like a medical doctor's work never ends, right? It's a commitment that you have, until when the medical doctor takes his or her oath. It's a commitment he or she has until, from the time he or she qualifies as a medical doctor until he or she dies. And in a way, we don't take an oath as a cybersecurity specialist, but it's sort of work that we have committed ourselves, right? And something that we have to continue doing for the public good. And so when we talk about the public good, there's a lot of work these days on AI, artificial intelligence, AI for good, right? AI for public good or AI for social good. So one of the questions I ask, and I gave a banquet address at the ACM CODASPI, the Conference on Data and Application Security and Privacy in August of this year. One question I ask is, can AI be for good in the midst of cyber attacks and privacy violations, right? Because with AI, right, you can have privacy violations because machine learning can put stuff together, lots of information, and be able to can infer using machine learning tools something that's highly private or highly sensitive, or the AI techniques could be attacked. So yes, without a doubt, AI is very important to whatever, it's enhancing human lives in terms of, giving us vaccines. I mean, they must have used some AI techniques to develop these vaccines. So, and for healthcare, for epidemiology, and so, but we also have to make sure that privacy is not violated. So it's a separate talk I've already given on data collection, data sharing, so policy aware data collection, data storage, data sharing, data analytics, and so on. And of course, it's adversarial machine learning or adversarial AI. Okay, so this is the talk for today. And my next talk is going to be on actual solutions that we developed. So again, what I'm doing now is taking some key talks I've given over the years. So one thing you've got to note that things have changed, right? Rapidly evolving, right? So, and my talk was up to 2013, but if you listen to some of my presentations on my YouTube channel, I give up-to-date information on some of the keynotes I've given recently. But what I'm going to do over the next 4 or 5 days is to select some of the key presentations I've given over the years, just so that we can maintain this history. And so that's what I'm going to give. So tomorrow I'm going to talk about some of the data mining solutions for malware detection. When I say tomorrow, my next talk, okay? So again, thank you very much. And please be safe, and hopefully 2021 will bring us good news with respect to COVID-19 and who knows, cybersecurity and terrorism. So anyway, but the thing is, the work has to continue. Okay, thank you.